Okay. Good afternoon. Who is taking notes today? Okay. Okay, we continue to discuss feature information and its importance in estimate, or its relevance for estimators and discriminators. Maybe I will remind you just of the expression for the feature information. I will write it here. So okay, this is the expression for the feature information. Both expressions are equivalent to each other. And we discussed the Kramer-Rao bound. For any unbiased estimator, the mean square error when the stimulus value is theta, for any way to construct the estimator, is at least as large as 1 over the feature information. And that's one place where the feature information is important. And moreover, we discussed the fact that when the observation is the sum over many independent observations, this becomes saturated. This really 1 over j becomes the mean square of an optimal estimator, which in this case is which is simply the maximum likelihood estimator. So I'll write it down. Okay, so this is what we did last time. Now I want to discuss discriminators. So what we imagine is now that for simplicity, we will consider a binary discrimination task. We have 2 values of the stimulus. And in each presentation of the stimulus, this elicits a set of observations, maybe neural, in our context, neural responses. And our task is to discriminate based on R. So the input is R. It can be a vector, it can be continuous, it can be discrete, depending on whether it's, say, the number of spikes or some observation which is a continuous variable. But the output is binary. One or two. the output of the discriminator. So a discriminator is really a function from the space of inputs to, it's like a dichotomy, from the space of inputs to a binary output. Okay, now when we discussed estimators, we had to decide how to quantify the performance of the estimator, and we made a somewhat arbitrary choice, which is convenient mathematically, which is to look at the mean square error. What about the discriminator? What is the goal for a discriminator?
Maximize the difference.
Which difference?
You get only one.
So you get one result. You just say whether it's theta 1 or theta 2. So what should be our goal? To get the correct choice. So it's, we're either correct or incorrect, right? If the stimulus is theta 1, we might say theta 1 and then we're correct. We might say theta 2 and then we're incorrect. So it's quite clear what we want to do. What we want to do is to minimize the probability of error, right?
So do we assume that both errors are lost in the same?
Okay, so there is one subtlety, which is we could in principle weigh differently errors if the stimulus is theta 1 and errors if the stimulus is theta 2. And therefore, even for a discrimination task, there is some space for decision. Maybe, when the stimulus is theta 1, we don't care so much whether we're making an error or not. When the stimulus is theta 2, we care a lot. Maybe. But therefore, there is some space for how to decide, but it's still much more well-defined in the case of estimators, and we will just assume that our goal is to minimize the average probability of error averaged over the two possibilities of the stimulus. Okay. Now, there is one thing that we need to define about the stimulus. Okay, so as in the case of an estimator, we would imagine that there is some stochastic or probabilistic relationship between R and the stimulus, but we also need to decide to say what, in principle, what is the distribution of the stimuli, whether one of them is more frequent than the other. So this is what we would call the prior. And I will denote this just simply by P1, 2, okay, where P1 plus P2 is equal to 1. And now, given this prior, the question is what would be an optimal way to construct the estimate, the discriminator. So if I tell you what is R, how would you decide if it's theta 1 or theta 2?
Do you know the right answer? I mean,
of course, I don't know if it's theta 1 or theta 2. This is why I need to try to discriminate. But I know. Yeah, I know how R. What is the relationship between theta 1 and theta 2 and the probability of all the different R's? Suppose that I know. Okay, so there is some probability of R given theta 1. There is a probability of R given theta 2, and I know this.
And the prior?
And I know the priors. So what do I need to ask? What do I need to ask in order to make an optimal discrimination? What?
The probability of error.
So I want to ask whether theta 1, so I observe some R's, and I want to ask whether theta 1 is more likely than theta 2. If it's more likely, I should choose theta 1 because then it will be, in more cases, I will make the correct choice than if I choose theta 2, right? So I will need to ask whether P of theta 1 given R is larger or smaller than P of theta 2 given R. Right? If this is larger than this, then over many cases where I observe this particular R, look, for a given R, I have to make a decision. I need to make a decision. If I see this R many times, the better decision for this R is to choose the theta which is more likely given this R, right? Because in more cases, I will make the correct decision. Okay, so this is very well defined. We can use Bayes' rule to write it a little bit differently. This is equivalent to asking whether P of R given theta 1 times P of theta 1 is larger or smaller than P of R given theta 2, P of theta 2. So now it's even more well defined because these functions we know, and we know the priors. So you see that the prior affects the way we make a decision. If theta 1 is very likely, then we will tend more to choose theta 1 over for the same activity, for the same observations. If theta 1 is more likely, we will tend more to choose theta 1 than if theta 1 is very rare. Okay. So this is the optimal discriminator. And just maybe let's look at it even a bit in more detail. We can look at two different limits. One is where we actually don't have any observations, or if the observations, the likelihood that the observations carry no information about the stimulus. Okay? In that case, P of R given theta 1 is going to be equal to P of R given theta 2. And all we do is just choose the stimulus which is more likely, right? In that case, makes sense, right? Okay, the other case, which is the one that we will focus on just for simplicity, is that we will assume from here on that P of theta 1 is equal to P of theta 2, so the two stimuli have equal probability. It's very easy to generalize everything that I will do to the case where there is a prior, which is not half-half. And in that case, we choose it's like maximum likelihood choice. We choose the theta for which the likelihood is larger, whereas this is posterior probability. Okay, so for simplicity, from here on, I assume that P1 equals P2. Okay. So now what I want to do is to ask what is the probability of error. So the optimal discriminator is very well defined. I want to evaluate its performance. Okay. So how do we do it? Let's first make a definition. I will define a function of the observations, which is the log likelihood log P of R of theta R given theta 2 minus log P of R given theta 1. delta log L. Okay, which is also the log of the ratios. And what is the decision rule in terms of this quantity? Whether it's positive or negative, right? So that our decision rule is to say that it's theta 1, it's theta 2 if delta log L of R is larger than 0, and it's theta 1 if delta log L of R is smaller than 0. So basically I have some function which is defined, a function over all possible responses, which is either, and if it's positive we choose 2, if it's negative we choose 1. All right. So now we need to think about the probability of error. So to kind of graphically think about it, let's assume for now that R is a one-dimensional variable, but of course it's typically not. It's a high-dimensional variable. So this axis, which will be R, you should think about it as schematically representing a whole high-dimensional space. But in the case where it's R-dimensional, it's a one-dimensional, I can plot, first of all, what I want to plot is the probability of R given theta 1. So let's assume that the stimulus happens to be theta 1. Okay? And given and what I want to plot now is the probability to get any given response given theta 1. So it might have some structure that looks like this. Okay, this is P of R given theta 1. I will write it here. And so the responses are drawn from this probability if the stimulus is really theta 1. But in order to make the decision, I now look at R and I need to compare P of R given theta 1 to P of R given theta 2. So actually let's put here a 2, because I just think it would be nicer if I put here a 2. Okay, because we choose stimulus 2 if this is positive. Okay, so the stimulus is theta 2. This is the responses are drawn from this probability, from this distribution. But I need to compare, when given the response, I need to compare this function to P of R given theta 1. So let's plot also P of R given theta 1. It will have some other distribution. Maybe it looks like this. Right. So now what is the decision rule? The decision rule is that I choose theta 2 if this is larger than this, and I choose theta 1 if this is larger than this. So you see that there is a separating point here, which would become a surface in the high multidimensional case. And as long as R is within this range, I choose theta 2. And when it's in this range, I choose this theta 1. So if theta is actually theta 2, I draw R from this distribution, and I need to ask what is the probability that I will fall at any point up to this point. Right? So this is the probability of making the correct choice. And the probability of making an incorrect choice is the likelihood, is if I choose theta from this distribution and fall beyond this point. So this is really the weight below this part of this plot, right? So this would be the probability of error if theta is equal to theta 2. And the probability of error if theta is equal to theta 1 from similar arguments would be the area under this part. Okay, so let's write it down explicitly. The probability to make an error given when theta is equal to theta 2 is equal to an integral over P of R given theta 2 and I need to look at the cases where this function is larger than this one. So I can write this as the Heaviside theta function of minus delta log L of R, where theta, the Heaviside theta function, is simply the function which is 1 when x is larger than 0 and 0 when x is smaller than 0, right? So this means that I'm calculating here the weight of the part, of all the r's, weight given by the distribution of P of R given theta 2 of all the r's for which delta log L is negative, because it's P of theta, the likelihood for theta 2 is smaller than the likelihood for theta 1. So this is the probability of error if theta is equal to theta 2, and the probability of error if theta is equal to theta 1 is an integral of P of R given theta 1 theta of delta log L of R dr, right? And the total probability of error will be half times P error theta equals theta 1 plus half times P error theta equals theta 2. Now, in practice, this might be a complicated quantity to calculate, these integrals. But what I'm going to do next is focus on a particular case where we can actually evaluate these integrals precisely. And this is half because on half of the cases, the stimulus will be theta 1. And then the probability of error is the probability of error for those cases, and half the cases it will be theta 2. And in principle, these two integrals don't have to be the same, right? The area under this part and the area under this part might look different. So what I'm going to do now next is consider a case where we can say something about these integrals more precisely. And this is a case where we have very close by stimuli. And we have many independent observations. And you will see how both of these assumptions play a role in the derivation that I'm going to do. So,
means that the stimuli themselves are almost the same?
yes. So the stimuli are it's like a fine discrimination task. like showing a bar and showing another bar which is only slightly oriented relative to it, or discriminated between tones that have very similar frequencies. So we have here quantities that look like the response given theta 2. We have both here and here we have the response, the likelihood of the response, the probability of the response given delta 2 and the probability of response given theta 1. And as you can imagine, since theta 1 and theta 2 are close to each other, what I'm going to do is I'm going to do a Taylor expansion. Okay? So I'm going to arbitrarily do the expansion around theta 1. I could just as well do it around theta 2 or around the middle between them, but I will do the expansion around theta 1. So I will write P of R given theta 2 as P of R given theta 1, well, let's put here approximate, plus delta theta times dP of R given theta 1 with respect to theta, or dP of theta with respect to theta at theta equals theta 1. And in fact, as you will see in a moment, we will need to go one order higher in delta theta. Okay, this will not be enough for us in order to estimate to understand the probability of error. We'll need to go up to second order in delta theta. And I will stop here. This will be enough. Okay. Now, you might ask, why? How do I know that I need to go to second order and I'm not continuing to third order? The point is that you will see that if I don't include this term, I will just not get any meaningful result. I will get a result that tells me that there's no discrimination there. I need this term in order to get some meaningful result. Okay. Now, the other thing that I will do is that because I have many independent observations, I will write that log P of R given theta is actually a sum over all these observations. So okay, so you can write this, and I can do the Taylor expansion for each one of these separately. And therefore, let's write delta log L right now, delta log L. So delta log L is the difference between P of R given theta 2 and P of R given theta 1. But this is just the difference between this and this. So delta log L, I can write as delta theta times sum over I d log P of Ri given theta to d theta at theta equals theta 1 plus half delta theta square times, and let's put here approximate, delta theta square sum over I okay, good. Okay, and I remind you again, if theta, let's assume, say, that theta is equal to theta 1, and then the probability of the decision rule depends on the probability, the decision rule is delta log L larger than 0, so the probability of error is a probability that delta log L is larger than 0. Okay, now how do we evaluate it? So delta log L is itself a random variable, right? In each experiment, there is a stimulus is presented. There are some responses, right? And delta log L is a function of these responses, so it's a random variable. What can we say about this random variable, considering the fact that it's a sum over many independent observations? It's what? It has a normal distribution. So because delta log L has this structure, we can say that when we have many independent observations, it's going to be distributed as a normal distribution. And that's great, because for a normal distribution, all we need to do to characterize it is to say what is its mean and what is its variance. And so I'm going to use this expression to evaluate the mean and the variance of this variable, and then I can do the integral which is written there. Okay? So,
Are you going to explain why you're going to use only this term?
which term?
You said did you mean we're going to use only the second order expression?
We're going to use the whole expression. I said is that I don't need to go to higher order. And this you will see in a moment why, what is important to see is that why we didn't stop at this stage of the Taylor expansion, because this would not give us yet a meaningful result. Okay, so you'll see that in a moment. Okay, so when the number of observations becomes large, then delta log L becomes is normal distributed, has a normal distribution. And this is a central limit theorem, and therefore, as I mentioned, we need only to write down what is the mean and what is the variance of this quantity. Okay, so mean. If I want to calculate the mean of this quantity, it's just a sum over all the contributions. So let's start with this term. So mu, the mean, so we need to calculate these terms. Do you know what we will get from these terms? 0. Okay, why? So the mean of d log p of r I given theta 2d theta at theta equals theta 1. What is it? It's an integral over all the responses of this quantity. Now the observations are independent, so for all the r components, for all the observations other than I, we'll just get a 1 from the integral. And then for the particular I, we have an integral dri, p of ri given theta, d log p of ri given theta to d theta at theta equals theta 1. So, but this is nothing but the integral. So maybe I should write it like this: d theta prime theta prime equals theta 1, and the integral is over r. Now this I can write as 1 over p of r I given theta prime. So I have here integral dri p of ri. Oh, and this is theta 1 here. Theta 1 times 1 over p of ri given theta prime, where theta prime is theta 1, so this just cancels this, times dp of Ri given theta prime to the theta prime equals theta 1. So this cancels. And now I can just take the derivative outside of the integral. So I have here the derivative with respect to theta prime, integral dRi, p of Ri given theta prime, all this evaluated theta prime equals theta 1. But this integral is just 1, right? So I have here a derivative with respect to theta prime of 1, and this is 0. So the mean of this quantity, of these quantities, is just 0. And this is why I needed to go to second order in the Taylor expansion. Now, what about this term? What is it? The mean of this term? It's minus the Fisher information, right? So what I have here is, so I get minus half delta theta square times sum over I, j, or let's simply write it as j of theta 1. Okay, good. Now, this is just the mean of this distribution of delta log L. I need also its variance. So, sigma square so I need to calculate the average of the square of delta log L and subtract the mean squared, right? Okay. If I take the average of this thing squared to leading order in delta theta, I will get this term squared, right? Then this higher order terms will only contribute higher order things. So I'm only interested in the leading behavior as a function of delta theta. So I will have something that looks like delta theta squared times the average of this thing squared and what will we get? So in the mixed terms, so we will have this sum multiplied by itself, right? You're with me? This sum, so we could write it as like a sum over I, sum over j, d log p of Ri with respect to theta, d log p of Rj with respect to theta. The mixed terms, when I is different from j, will give me 0, just as what I did before. But when I and j are the same, then this thing is a square of something. Of course, its average cannot be 0. It's an average of something which is always positive. And what will it be? The average of d log p of r given theta to the theta squared. What is that? What? It's also the Fisher information. It's the other expression for the Fisher information that we wrote in the beginning of the lecture. So I will have a sum over all the neurons of this thing, so it will be the total Fisher information. So we'll have here also j of theta 1. And in principle, I need to subtract now the mean squared. But you see that the mean is of order delta theta squared, so the mean square is already of order delta theta to the power 4. So I can, under our assumptions, I can neglect it compared to this term.
Would there be an n there? Because
So this is the total Fisher information.
I choose the n.
So j is like for all the observations. This also here.
Yeah.
Okay, fine. So now we have so this is now with there are of course corrections which are higher order in delta theta, but I will not worry about them right now.
Why do we neglect
Because the mean is order delta theta squared. So squared it's order delta theta to the power 4. So it's small compared to something which in the limit where delta theta becomes small, it will become negligible. Okay? All right. So just to draw this, I could ask myself, what is the distribution of delta log L for different values of delta log L, okay? And under the assumption that theta is equal to theta 1. And you see that it has a mean which is negative, and it has a variance which is, of course, positive. And we're in the limit where the central limit theorem holds, so it will look like some Gaussian, where this is mu, and this, the width, is sigma. And the probability of error is now the probability that delta log L is positive, which is this tail. Right? So it's good that mu was negative. This is what we should expect. That they have, on average, we're making, if theta is theta 1, on average, delta log L will be negative. We will typically make the correct choice, but we need to calculate the weight of this tail. And you can see what happens as we have more and more observations. If we have more and more observations, J is proportional to the number of observations, right? So the mean becomes, more and more large. The variance increases too, also proportionally to n. But that means that the standard deviation only increases in proportion to the square root of n, right? So as the number of observations becomes larger and larger, this Gaussian gets shifted to the left, and it's relative to its mean, the width of the Gaussian becomes smaller relative to the mean. And therefore, the probability of error will become smaller and smaller. Okay? Now we can write down what it is explicitly.
The variance increases, right?
Yes, both the mean and the variance increase, but the standard deviation.
Right.
Yes, but relative to the mean, all we care about. So this is. So this will be a small number of observations, and this would be, let's say that we quadrupled the number of observations, then the mean will become 4 times larger. The width will only become 2 times larger. So will look something like this. And the probability of error will be smaller. Okay. So it's true. If I would draw it scaled by n, it would become the mean would become at the same place, and the width would become smaller and smaller, like 1 over square root of n. All right. So let's write down explicitly the probability of error.
I'm not sure.
If this is the variance, and we said that J becomes larger and larger,
Yeah.
then does it mean that the variance increases?
The variance increases. Standard deviation. So the mean increases proportionally to the number of observations. Variance also increases proportionally to the number of observations. Standard deviation increases like the square root of the number of observations. So the ratio between the standard deviation and the mean becomes smaller and smaller. And this is all that matters for the weight of this tail. This tail does not care if I would multiply mu and sigma by a constant, the weight over the tail would not change. But if I increase mu and I increase sigma less, then there's less probability in this tail. So let's write this down explicitly again. So the probability of error given when theta is equal to theta 1. So I'm stealing a few minutes from Neta. Is equal to the integral from 0 to infinity. I need to write now the the distribution of the normal variables. So let's call it dz. Z is delta log L, square root 2 pi sigma squared, exponent minus z minus mu squared divided by 2 sigma squared. That's all that we need. And this is what is called, more or less, a complementary error function. Now, but before I write it explicitly in terms of the complementary error function, one thing to note is that this is some function. You can see just from scaling arguments that this is some function of mu divided by sigma. Okay? This is what I said in words before, that if I would multiply mu and sigma by a constant, it wouldn't change this integral. But if what happens when we increase the number of observations is that the ratio mu over sigma changes, becomes larger, right? Because mu increases as n, and sigma increases as square root of n. Let's write. So let's write. And mu over sigma, what is it? Mu over sigma, you see that it's delta theta. It's half delta theta times the square root of j. Right? So going back to here, this is equal. Now we just need the formal definition of the complementary error function. So I will, you can see how the complementary error function is defined. It's defined through an integral like this, but there's a factor half in the definition. So this is half the complementary error function of. And now I'm going to write it just in a way which is commonly done in the context of discrimination tasks. It's half the complementary error function of something which is called d prime divided by 2 square root of 2, where d prime is delta theta square root of j. This is just a definition. And this is called the discriminability. So how does this function look like as a function of d prime? So when d prime is very small, we have here half the error function of a very small variable, and for very small variables, the complementary error function approaches 1. So the probability of error is half. And it goes down as we increase d prime. So it goes like this. So if in the limit where delta theta approaches 0, if delta theta is 0, then there is no difference between the two stimuli. So of course our probability of error must be half, right? And if delta theta is finite, the more, say, observations we have, or the more informative the observations are about the stimulus, the larger d prime will be, and we will have a smaller error.
Can you explain this equality?
Which equality? This one? It's just the definition. The tail of a normal distribution like this is called the complementary error function, and you can look up the formal definition in the in a definition in a table of mathematical functions. It's just a definition. It's just that in the definition you need to, the way it's usually defined, you need to do some change of some small changes in order to get this to see that it's half and like this. But it's basically their complementary error function is an integral of a Gaussian from some finite point to infinity by definition.
And how did you extract d prime?
Well, I told you, okay, it's obvious just even without knowing how to calculate or to express this integral, it's obvious that it has to be a function of mu over sigma. And you can, by the way, you can check it explicitly by just redefining z and c from scaling arguments that it's, you can, you know, take out one of these variables and get some dimensionless integral which depends only on this ratio. And then it's just a matter of looking in how the complementary error function is defined and writing it in terms of these variables, and you see that that's what you get. Okay, so, but you see that it's indeed a function of delta theta times square root of j. Okay. So this is how this function looks like. Now, if I would say plot it, the probability of error as a function of delta theta, then of course it will look the same. But the important thing to note is now the width, the characteristic value of delta theta over which this really goes to zero is 1 over square root of j. Right? So this tells you something important. It tells you, say, that if you increase, say, by a factor, if you multiply by a factor of 100 the number of observations that you have, you will be able to discriminate stimuli which are 10 times more close to each other. Right? No?
But is that true in reality?
Well, in some cases, yes. It depends on whether we can do optimally. If you do optimal maximum likelihood discrimination, then yes, it's absolutely correct.
Assuming independent of what also.
Yes. Also, if you have independent observations,
This was laid down in reality faster, no?
probably, but also if we say do a psychophysical, so you know this concept of D prime discriminability is used in psychophysical experiments, and this plot is something like what is called a psychometric curve. You plot what is it, you say do an experiment with a subject, and the subject needs to do discrimination, and you plot what is the probability of error as a function of some parameter that you will change. And to say that this plot should describe correctly a human psychophysics, we need to make several assumptions. One is that in the different experiments, the errors are completely independent, or the noise is completely independent, and that is might be true and might not be true. There might be some internal variables in the brain which are varying over long time scales and are causing some not independent noise. And the other thing is that we need to assume that the brain is optimally doing the discrimination, which might also not be the case. But this at least tells us what we should expect for optimal discrimination. And it's also relevant to many other contexts of just, you know, how do you do discrimination based on noisy data and what you can expect your error to your probability of error to look like. Let me see if there's any other comment that I want to make. We calculated here the probability of error given theta 1, that the stimulus is theta 1. What would be the probability of error if the stimulus is theta 2? The same. In principle, you see here that we have here j evaluated at theta 1. So we would need, the only thing that will change in this derivation, so there will be some signs that will change, but they will all turn out to give the same result. But the j will be evaluated at theta 2, but because we assume that theta 1 and theta 2 are close, j of theta 1 and j of theta 2 are the same. The difference between them would give terms of higher order in delta theta. So we might as well just write here j, and it doesn't matter here if we put here j of delta theta 1 and theta 2. So phi of error given theta 2 will be the same. And therefore, that's also the probability of error if the stimuli have equal probability. One other comment just about the derivation is that we assumed that theta is equal to theta 1. and did the expansion of delta log L and of P around theta 1. We could have done it differently. We could have, just in the derivation, we could have said, let's assume that the stimulus is theta 1 and do the Taylor expansion around theta 2. And then several things would change in the derivation. It's a nice exercise to think what would change and convince yourself that in the end you will get the same result. Okay? And so I just want to summarize what we did about Fisher information. So the Fisher information is a function of the stimulus. And it really tells us something local about, you can see also in its definition, it will tell us something local about how the probability of responses depends on small changes in the stimulus, right? Because the expression for Fisher information involves derivatives at that particular stimulus, it's really telling us something very local. How do the responses change when you slightly change the variable? And accordingly, it tells us something. That's one of the reasons it gives us only a bound for an estimator. So it gives us a lower bound on any unbiased estimator. The probability of the mean square error is at least as large as 1 over j. It tells us what is the maximum likelihood, and this is saturated